Welcome to Intro2Astro 2024.
Yeah. So hi, everybody. I'm Drew, and I'm a grad student at McMaster University up in Hamilton, near Toronto. So I study exoplanets, specifically rocky exoplanets around dwarf stars. And so that's part of the reason I'm so excited to be able to talk to you guys about radial velocities today, which is how I go ahead and find these exoplanets. And then the model fitting, which is what I do with the data once I get it. So yeah, I guess I'll get started.
Yeah,
So I'm covering two different topics today. The first topic I'm covering is model fitting, about using Markov chain Monte Carlo methods to fit data. And then the second topic I'm covering is radial velocity and how we model it. But first, we're going to be talking about Markov chain Monte Carlo fitting. Feel free to ask any questions in the chat if you guys have any while I'm talking. I can't screen share.
give me one moment. Sorry.
Yeah, no worries.
Okay, should be able to do it now.
All right. Can you guys see the screen?
Yeah, go ahead.
Perfect. So yeah, I'm going to be teaching you guys about Markov chain Monte Carlo fitting methods and how they work. So just a quick note before we get started. This presentation is mostly intended to teach you guys about the math and ideas behind how this model fitting works. Alongside this, I've included a demo, which will give you a little bit more of an in-depth look into the actual implementation of this in Python. And then there's an assignment later on for if you guys are interested in exploring that yourself. But I think understanding how it works is something you need to do before using it. So let's jump right in. So imagine we're in a situation where we have a model that we want to fit to data. We have a set of data points. We know what form the model takes, but our model depends on some sort of parameters. It could be if you're modeling exponential growth, it could be your initial conditions. If you're modeling a planet, it could be the orbital parameters of that planet. So we know what form our model takes. We don't know what parameters the model fit the data the best. So how do we figure out what parameters fit our data? So there are a whole bunch of different ways to do this. But the one I'm going to focus on is probably the most common one that you'll use in astronomy. It's called Markov chain Monte Carlo fitting, also called MCMC fitting. So let's go ahead and talk about how it works. So let's take an analogy to start. Imagine you're in the dark on a foggy hill. The hill's bumpy and the fog is kind of thick, so you can only see right around you. The goal is to reach the top of the hill so you can get above the fog. You can't just see where it is. So how do you find the highest point you can? This is ultimately what all sorts of model fitting codes are designed to do. You need to figure out what location, if not in real life, in parameter space, fits your data the best, and you want to get up to the highest point. You could just, test out a million different random sets of parameters and see what the best fit of data is, but that's super inefficient, and that'll take your computer forever. So instead, let's say you start out at some current location, where you are right now in the middle of that fog. And let's say you take a look at the ground right around you to figure out what direction will take you the highest for each step. So what direction will be the best, will improve your fit the most. And then you walk in that direction, and then you check again. After you take a step, you see which direction now will get me the highest. And it'll take you higher where you are now. If you keep taking steps in the direction of the maxima, as far up as you can get, eventually you're going to get further up than you are now. But then you run into a little bit of a problem. So what if you reach a local maxima, a little peak that's still not the highest point? Then you won't go any direction, right? Since staying still will let you move the highest, but you know you can get higher than where you are. So maybe you look around and you decide that every once in a while, you'll take a step downwards. Not often, but often enough that you can take a step down off from that local maxima and continue wandering around until maybe you reach the next hill over and you can get higher than where you are right now. that's how Markov chain Monte Carlo fits work. A Markov chain, or the Markov chain part of that name, it just refers to the fact that you take some part of parameter space and you randomly pick a direction to go in, meaning that you'll occasionally take a step downwards. The Monte Carlo part of the name means that you do this in what's called a Monte Carlo simulation. What that means in computer science is you just do the same experiment with different starting conditions or maybe different random seeds over and over and over and over, and then you look at the aggregate of where all of them go. So let's drop the analogy for a bit and let's get into more detail. So I'm going to try to include as little math here as possible. Some math does need to be used just because it is a mathy process, but the math is also super complex, so I'm going to try to keep it light. So a Monte Carlo Markov, or a Markov chain Monte Carlo fit uses what are called walkers. So just like the person trying to get through the fog before, a walker is a set of positions that your model explores, beginning at whatever spot you decide. You'll typically have dozens or sometimes even hundreds of walkers, depending on how many parameters you're trying to fit for. At each step of time, or all at once, all of these walkers will take a look at where they are and pick a random direction around them in parameter space. How they pick a position around them, it depends on exactly how you're implementing it, but say they just pick a random direction. Then each walker takes a look at that new direction and sees if the new direction it's about to go is going to improve your fit. So the way it does that is it calculates what's called the log likelihood of your model at that point, or with those parameters. Essentially the logarithm of the likelihood that your model will spit out the observed data. And because we're using logarithm, that means that if you're at this new point, a higher log likelihood means that your model is a better fit to the model. Your model is more likely to spit out the observed data. So if your walker takes a look at that new point and it sees that this new location is going to be a better fit, it's going to have a higher likelihood, then a walker is going to move to that new location, right? And so if you just keep repeating this process over and over, that's the same thing as you continuing to look every step in front of you and seeing which direction will get you the highest up. But like we said, this is a Markov chain process. So if the new spot is a worse fit, if the likelihood is lower, then it will still have a random chance of moving to the new location, depending on how much worse the fit is. So if the fit's only a tiny bit worse, there's still a pretty good chance the walker is going to move to this new location. But if it's a lot worse, then it's probably not going to go there. So each walker will pick a new location and decide whether or not to go to that new spot. You can do this for a whole bunch of walkers, or your computer is, and then it's going to repeat this process for a long time. It's going to repeat this cycle over and over and over, thousands and thousands of thousands of times, or sometimes hundreds, but a lot of times. And then you can just look at the aggregate of all the paths these walkers go. Typically, all these walkers should converge onto the best fit. Same as if you keep doing this hundreds and hundreds of times, you are eventually going to find the best spot, the highest spot on this hill. Does that make sense so far?
Yeah, definitely.
Okay. Perfect. So that's all well and good, but we're kind of avoiding the actual math. We're just talking about how it works. How do you calculate a log likelihood? So let's talk about it. All these sorts of fits are based off of something called Bayesian statistics, which Bayesian statistics are centered around calculating probabilities and informing these probabilities based off of previous data you have and what you believe. It's really annoying when you have to figure out all the math involved, but it works. But using Bayesian statistics and like the back end of how these models work ends up working really well when you're trying to figure out distributions of parameters, which we are here. So all of Bayesian statistics is based around something called Bayes' rule. And so Bayes' rule essentially tells you that given two events, event A and event B, Bayes' rule tells you the probability of event A, given that you already know event B is happening, which is often written as this, like I just sent in chat. That's a probability of event A given event B is equal to this equation right here. The probability of event B given event A times the probability of event A divided by the probability of event B. Where we get that equation from and what its applications are outside of this, we're not going to get into because that is an entire course on its own. But it can be really useful when we think about what these two, or what event A and event B are in this context. So if we just swap those names around and we replace event A with what we call here event H, the probability of our model being the true model. And we replace event B with event D, meaning the probability of our data being the actual data we observe, we can just go ahead and plug it in, or plug all those Bayes' rule in, and get this big equation that I'm showing on the screen right here. Of course, this is still probably super confusing because all I've done is swap names around, but it turns out that we can calculate most of these different values. This value over here, the probability of H given D, so the probability of our model being the true model, given our data is correct, is called the posterior. The posterior is essentially the likelihood of your model being the correct model, given the data we have. Or the likelihood that your parameters are correct, given the data you have, too. This is a value that we want to maximize in our fits. If we can find the parameters that have the best posterior, then that is the best model. Make sense? The other values here are all values that we can calculate to get our posterior. So first off is the probability of our data being correct, given the fact that our model is correct. This is what's called the likelihood. The likelihood essentially tells us that essentially tells us how well our data fits our model. That is, assuming our model is true, how good a fit is the data to the model. So this is something we can normally calculate if we know exactly what our data is and what the uncertainties in the data are. And we're going to get more into that later. But suffice to say, we can calculate that value. The probability of our model being correct is different. This is what Bayesian statistics does. This is why Bayesian statistics is important. If we know what's called the prior, the probability of our model existing in the first place, then we can use it to inform our data. So say if we had two models, model 1 and model 2. Model 1, it uses parameters that we think are realistic, and the numbers, and the form of the model we think is completely realistic. Model 2 fits the data a little bit better, but all the numbers are really weird, and the parameters aren't what we expect them to be. We want to kind of ignore that, right? We want to be able to get rid of a slightly better fitting model in favor of one that makes a little bit more sense, essentially. And so that's what the prior is. The prior tells us what our likelihood of the model, what our initial likelihood that our model is correct is. So Akriti asked, somehow the part where we have the probability of how likely our model is in the first place, don't we assume our model to be true? What are we measuring this probability against? So this is a really good question. So yes, this does assume our model form is true. What the Monte Carlo Markov chain does is it tells you, or it compares different parameters for models. So it finds the best fit of individual parameters for a model. This won't let us compare against different sets of models. For example, if we have a set of data and we're trying to compare, linear growth versus exponential growth, we can't necessarily compare those. Well, we couldn't easily compare it using this method. But if we had, say, quadratic, Okay, sorry, let me rephrase that. Sorry. So let's say we had two completely different models that use different forms. We are trying to compare like a sinusoidal wave to a linear growth and trying to see which of them fit the data better. Those are completely different models, and those wouldn't fit our data well. And we couldn't use the Markov chain Monte Carlo method to compare the two. But if we were trying to compare to figure out, say, does the line y equals x or the line y equals 2x fit our data the best, then that's what this would be good for. So this won't let us compare entirely different models, but this will let us fit for the best parameters of a model. Does that make sense? I'm sorry, I think I explained it a little confusingly.
Yeah, that makes sense.
Perfect. So yeah, so we talked about the likelihood here. That's how well our model fits our data. And we talked about the prior, which is how likely our model is, or these model parameters are in the first place. This last one is what's called the evidence, the probability of your data actually occurring. We can kind of ignore this one. That one is really hard to calculate, but you're comparing the same data to different models. So whatever this value is, it's going to be the same for whatever models you're comparing. And so we can just kind of ignore this, which means that we just want to maximize the product of these two likelihoods, or of those two probabilities. So the reason that we go ahead and calculate the log likelihood and the log prior and the log posterior is, well, there are two different reasons. One is that the probabilities that work with can get like absurdly small. It's the point that computers can have trouble working with them if they're not careful. And a logarithm brings them down to realistic, or to numbers that are a lot easier to work with. A logarithm will turn a likelihood of 10 to the power of -10 just to -10, which is a lot easier to do math on. But more importantly, the reason we use logarithms is that the log of two values multiplied by each other is just a sum of the log of 1 plus a sum of the log of 2. So we know the posterior here equals the likelihood times the prior divided by the evidence, but we're going to ignore that. But if we just turn that to logarithms, we just realize, or that goes ahead and shrinks down to just the log posterior, which is what you calculate, or which is what your computer calculates, is just equal to the sum of the log of the likelihood and the log of the prior. So if we have functions where we can calculate the log of the likelihood and the log of the prior of a set of parameters, we can calculate our log posterior. Does that make sense? All right. So first of all, our log likelihood. There are a whole bunch of ways to calculate log likelihood. We are going to quickly talk about log likelihood in the most common case. If your data are all completely uncorrelated with each other, then your log likelihood is easy to measure. Normally, you take your measurements for like whatever your data that you're trying to fit at different times from each other. And so this is usually the case, right? In the interest of time, I'm going to skip all the math behind it, but I will provide it if anybody would like. But suffice to say, normally when you calculate the log likelihood of your data, you will use what's called the chi-squared log likelihood. So if you have a set of data, call them y, and a set of uncertainties, call them sigma, then you can just go ahead and calculate the log likelihood with this equation down here. You take the difference between your data and your and your model, you square it, and then you divide by your uncertainty squared. Then you add all those up and you multiply by -1/2. So again, without getting into the math behind it, what that does is that the log likelihood is highest if you can minimize the difference between the model's estimate of the data at a given point and the actual data at that point. If you can do that, you increase the log likelihood. But it doesn't punish being as wrong as harshly if you have really high uncertainties in your data, or if the actual data values are higher. Like being off by 1 when your error is 10 isn't as bad as being off by 1 when your error is 0.1. But the other thing that we need to worry about are priors. So how do we calculate those and how do we implement those? So like I said earlier, a prior probability represents what is originally believed before new evidence is introduced. Whereas a posterior, what your computer calculates, is what happens when you actually is the likelihood once you actually take that new information into account. These priors can take many different forms. You can have initial beliefs about what data or about what numbers your parameters can take based on maybe what's physically possible, or these priors can be derived from, say, prior work on similar data. So say you're trying to fit for the mass of a planet with some data. You know the planet has to have a mass larger than 0 because it can't have a negative mass, right? And it has to have a mass of, say, less than the sun because it's not a planet once it's the size of the sun. But other than that, you really have no idea what the mass might be. And you'd have no reason to prefer a result of, say, 1 Earth mass to a result of, say, 10 Earth masses. In that case, you might want what's called an uninformative prior, one that doesn't really affect the results. So in this case, an uninformative prior, or a uniform prior, might just say, my model, or my prior, has an equal likelihood if the mass of this planet is between 0 and Earth masses, and the mass of the sun. But the model cannot find a value outside of that. The likelihood is negative infinity. And so that would be an example of an uninformative prior. It's just something based off what's physically possible, and it's a very wide prior, wider than you expect, or wider than the real value you're expecting to find. But you also might have an informative prior, a prior derived from prior work. Say you're studying that same planet. A previous paper you read used different data and found a period of the planet of 10 plus or minus 1 days. You have new data you're working with, or you're doing something else that just needs that period, but you still need to input the period as a parameter to your model. In that case, you might want an informative prior, which says that, well, I have a likelihood that follows a Gaussian distribution with a mean of 10 days and a standard deviation of 1 day. And so that means that even if a period of, say, 1,000,000 days fits your data a little bit better than the period of 10 days, you're more likely to select the period of 10 days because you have a much stronger prior on it, meaning you need a lot of evidence to take a value of 1,000,000 days as true. And I'm not showing equations for priors because there's a whole bunch of different forms priors can take. Uniform priors and uninformative priors. Well, uniform priors usually have a uniform distribution, but informative priors can take entirely different distribution shapes depending on where you're getting those numbers from. So I'm intentionally trying to be vague here. So does anybody have any questions at this point? I understand a lot of what I'm saying is kind of confusing, and there's a lot to talk about. It's a confusing subject, I promise.
Yeah, perhaps things will come into focus after you talk about the radial velocity, like, having the motivation in the background.
That's fair. That's fair. And once I talk about that, hopefully it'll provide a good example.
Yeah, maybe we can pause for questions when you're done with the second part.
Sounds good. So yeah, so the very last thing to talk about is what do you actually do while you're running or while you're calculating these posteriors. You've wrote some code to set up your walkers and start to get them to try to find the right parameters. And your fit is running. Your code is running, your model's working, but how do you know when it's finished? So in short, a fit is finished if the chains you're fitting, or if the walkers you're fitting have converged. Without getting into the math, that means that all your walkers, if you look at a graph of where they've been over time, they all follow a similar distribution, and they've all explored enough parameter space in a way that makes you confident they follow the true best fit distribution. Now, this can be tough to show because it's really hard to prove mathematically that something is converged, but we can still get an idea of what that looks like. So here is what's called a chain plot. This is a plot of all of our little walkers and what parameter values they take over time. This is one that you'll see. This is one from my actual demo, which is trying to fit a few different parameters, period, or the period and the radius, for example, of a planet over time. And so you can see each of these walkers look like little gray lines. And you can see after exploring around for a little bit, they all kind of converge straight to the same value. The same thing happens for the period. They all move around a little bit, and then they all find the same best fit value as a fit runs for longer and longer, which is good. That tells you that a fit is working well. And the other thing, the very last thing I want to show you is how you can visualize your results. All right. This over here on the right is what's called a corner plot. This corner plot shows a few different things. If you look along the diagonal, you'll see what look like 5 different sort of like normal distributions or Gaussian distributions. Each of those show the distributions of the walkers in parameter space for each parameter. So you can see the radius of these planets, or of this planet that we fit, seems to be centered around this value right here, but it sort of follows the Gaussian distribution. And over here, we can see what looks like a comparison of the distribution for each pair of parameters, which lets you visualize any sort of correlations between parameters. For example, we can see a correlation between these 2 parameters here. If we find a higher value for one, we're more likely to find a higher value for the other. And so ultimately, that is the goal of an MCMC fit. Our goal isn't just to find the best fit value. If we wanted to do that, there are much easier methods we could use. But an MCMC method, or an MCMC fit, lets us figure out what the distribution of possible parameters are, which is ultimately what we want when we're trying to fit our models to data. So yeah, I haven't gotten into any of the code behind how this works, but I have provided a demo for you guys, which I think should be available to you. And if not, let me know. Which should walk you through how to get the setup in code and have you test it on real data from the Kepler Space Telescope. So yeah, that's all I have for model fitting now. Does anybody have any questions?
Yeah, in the interest of time, let's move on to the second part, and let's deal with questions after that.
Yeah, that's totally fair. Let me share that too. So the other topic that I'm covering today is radial velocities. Radial velocities are one of the most common ways to detect exoplanets. And so I want to talk to you guys about how this method works and how we can find exoplanets. Once again, this will not get too much into the code behind it. The demo, which I've also provided here, will give you a more in-depth look into the actual process of how you turn data into actually getting masses of planets. But once again, I think understanding how it works is something you need to do before using it. So let's get started. So yeah, the radial velocity method of detecting exoplanets, also called the Doppler method, is the earliest method of detecting exoplanets. It's the very first one that we used to discover planets around a main sequence star. So have you guys heard of the Doppler effect?
Yeah, we talked about this briefly earlier in the workshop when we were talking about exoplanet detection methods.
Oh, perfect. In that case, yeah, very briefly, just in case there was anyone who missed that. The Doppler effect is what happens when something is emitting waves while heading towards or away from you. So you might be able to hear this when you hear like a fast car rush by you, and it makes like a sound, because the sound are the waves in air that are kind of getting compressed as the waves move, as the source of the waves moves towards you. But it also turns out that the exact same thing happens to light coming from stars. So as a planet orbits a star, it's going to move around a lot, but the star will wobble a little bit too. Like as a planet circles a star, it's going to trace out big paths around it because the star is exerting gravity on it. But the planet is going to exert gravity on the star too, and that's going to make it wobble around a little bit. And importantly, the heavier a planet is, the more gravity it's going to exert, the more it's going to make the star wobble. So if we had a way of seeing how much the star wobbled, we could figure out how heavy this planet is. And it turns out that there is a way to do that. So stars emit a lot of light. And it turns out that light undergoes the exact same Doppler effect that sound does. So as a planet circles a star, the star is going to trace out smaller circles from the gravity due to the planet. And the light is going to change frequency in the same way that sound changes frequency. But the frequency of sound, or the frequency of light, is just the light's color. And so as the star wobbles back and forth, the star's color is going to change, getting a little bit redder or a little bit bluer. And so luckily for us, there's a really easy way, well, comparatively easy way, to measure how much redder or bluer a star is getting. So when observing a star, we can measure its brightness as a function of wavelength, called its stellar spectrum or stellar spectra. Normally, we would expect the spectrum to look smooth, but when we look at it, we see really thin peaks and really thin valleys in that brightness curve. And those are due to the presence of atoms or molecules inside a star. Each atom or molecule has its own little wavelengths of light it absorbs really well if it's cold, or emits really well if it's hot. And so light of all wavelengths gets emitted by the star, but the atoms inside the star's outer layers interact with that light. If the atoms are colder in the inside of the star, they absorb their own special wavelengths of light, causing dips in the spectrum of different wavelengths. And these are really, really thin dips, importantly, like a fraction of a nanometer wavelength. And on the other hand, if those atoms are hot enough, they emit at those same wavelengths, causing peaks in the spectrum. So if we have really nice, easily identifiable sharp lines in the spectra, we can see them move, shift to the left or right, to the red or blue, a lot more easily than we could see the entire spectrum shift to the left or right. So if we figure out how much they're shifting, we can figure out how much the star is moving, and then we can figure out how heavy the planet is. So let's see what that looks like. This is a sample graph of the radial velocity of a star over time. For most planets, a radial velocity curve will look really similar to a sinusoidal curve. A plot of the radial velocity over time, a radial velocity graph, is entirely described by just a few different parameters. So there are 5 parameters of a planet that can describe its radial velocity effect of the star. The period of the planet, the semi-amplitude of that signal, the time of transit, and then the eccentricity and the argument periapse. So let me get into what these are. The period P is probably the simplest. The period is the exact same as a period of a wave. It's the time it takes for a radial velocity cycle to take place, for a planet to make one orbit around the star and begin the same curve anew. So it's the different distance between peaks of that curve. The time of transit, T0, is the epoch. That tells us at what time does a planet transit. And that has the effect of shifting the radial velocity curve to the left or to the right. So normally at an epoch T0, when the planet is transiting the star, the planet is just straight up pulling on a star, and so it's pulling on a star straight towards us. But if you look at the circle that the star traces out, the star is moving tangentially to us right at that time. And so the radial velocity curve is 0, but increasing. So like right here, we would expect to see a transit if the planet were transiting. The semi-amplitude, meanwhile, K, is analogous to the amplitude of the wave. It's the distance from the center of the wave to the peak, like this. The important thing with a semi-amplitude is you can actually use a semi-amplitude to get the mass of the planet using this equation right here. Alternatively, if you want to break it up into more common units of Earth and solar masses, and meters per second of the signal, you can have it rewritten as this. I got kind of cut off there. The important thing that you want to worry about when dealing with this mass you would calculate here, is that the mass of this planet is actually what's called the minimum mass, or m sin I. So think about it like this. If a planet has a very steeply inclined orbit, as in it's not transiting, it's not edge on, it's like closer to face on, then the star won't just wobble straight forwards and away from us from our point of view. It's going to wobble radially, but it's also going to wobble tangentially. So forwards and backwards, but also up and down. And so that means we're underestimating the size of that wobble. And so we'd be underestimating the mass of the planet. It's really hard to figure out what the inclination of a planet is, or how inclined the orbit is. If a planet is transiting, then we know the inclination is very close to edge on. And so the minimum mass is very close to the actual mass. But if we don't know it's transiting, it's really hard to figure out the inclination. And so in a lot of papers that tell us about the radial velocity of a planet, or get the mass of a planet from radial velocity, if it's not transiting, they'll just tell you the minimum mass of the planet instead of the actual mass. Which sucks, but it's really hard to get a more accurate estimate than that, so we can only kind of do what we have. The other two parameters, the eccentricity and the argument of periapse, are a little trickier to recognize. The eccentricity essentially describes how far away from circular the planet's orbit is, and a high eccentricity has the effect of making the planet's orbit less sinusoidal and more spiky. So you can see what this looks like for a whole bunch of different eccentricities and a whole bunch of different argument of periapse. You can see what a sample radial velocity curve might look like. For a perfectly circular orbit, this looks sinusoidal. But for a really eccentric orbit, the RV curve looks really, really spiky. The argument of periapse, meanwhile, rotates the orbit in space, so it kind of determines where along the orbit those spikes occur. And it's really hard to describe what an eccentric orbit looks like, aside from being spiky, for good reason. It turns out that for orbits with non-zero eccentricities, you can't actually model the radial velocity curve with a simple equation. Code actually has to model the orbit at each time to figure out what the radial velocity is. Luckily for us, though, most planets have pretty low eccentricities. This isn't a huge issue in practice, but you can still see what different radial velocity curves look like for different eccentricities and see how they change. And of course, this is normally just one signal out of many. So if you have multiple radial velocity signals, say you had two different planets in the system, you could add those two signals together just to get the final radial velocity curve. So you can see here a tighter, smaller period sinusoidal signal, probably from a planet, and then a much longer period one, probably corresponding to another planet. The reason I say probably is because it turns out that this is really tough to do in practice. Like we looked at this equation here, it's easier to, or just by looking at the power relationships that the mass of the planet and of the signal have with, say, the mass of the star, or the mass of the planet, or the period, we can get an idea of for what planets radial velocities work well. Radial velocities, this method works really well for big planets and for small stars and for really short planetary periods. Now, of course, the same thing is true as transits. It works really well with big planets and small stars and short planetary and short periods. But ultimately, it's really tough to get around that. The very first planets that we ever discovered, main sequence planets, were discovered with this method. But those sorts of planets that we were discovering really early on were a type of planet called hot Jupiters. Really hot planets, really big planets that were really close to their star. And those are ideal for radial velocity methods. But it's really hard to find smaller planets, like say an Earth. So when looking at this plot right here, we can get an idea of what the typical uncertainty on a radial velocity measurement looks like. We can see we're getting radial velocity measurements that fit this model pretty well, but the uncertainties are on the order of a meter per second. On the order of a meter per second of movement of the star is about the best we can get. Now that sounds pretty good, and it is pretty good. But then you realize that if you go ahead and do this whole calculation, you kind of rearrange it to get the semi-amplitude on one side and calculate what the semi-amplitude of, say, the Earth is, the Earth's radial velocity signal is about 10 centimeters per second. So yeah, we're not really detecting Earths right now. Not unless they're really close to their star. So for a planet to have a large enough signal to be detectable, it needs to be big, close to its star, or have a small star. But maybe you could just say, oh yeah, we can just get more data, or we can just, stare our telescopes at these stars for longer to get more precise measurements. And we can, but we start to hit diminishing returns. And that's because of stellar activity. So I hate stellar activity. Stellar activity is what I spent my entire grad program fighting with. And it is a reason we have kind of not hit a limit, but we're hitting diminishing returns as far as getting more precise radial velocity measurements goes. So stellar activity just refers to the various processes going on in the star that can cause either spurious measurements or imprecise measurements. So there are a few different forms that they can take, but generally there are two different ways they can mess up the measurements. First off is stellar activity from what's called granulation. Granulation refers to all the paths of plasma that occur in the star and bring material up to the surface of the star and away from the surface of the star. But you might notice that if it's bringing stuff up to the surface of the star, that's towards you, and if it's bringing stuff away from the surface of the star, that's away from you. And so that will kind of mess up your measurements, because while the planet is trying to induce its own signal and cause everything that's emitting light in the star to move towards or away from you, everything in the star is kind of moving towards or away from you on its own. And so what this can do is it can induce variability on your measurements on the order of like 1 meter per second, which is about the uncertainty that we're hitting right now. The other type of variability is called star spots. Star spots are dim parts of the star that rotate around with the surface of the star. They can exist for days or weeks or sometimes months. But the important thing is that these stars, or these sunspots, can cause periodic signals in your radial velocity measurements that look an awful lot like planets. A star, depending on your star, it can orbit with a period of multiple days, or even dozens of days, which is a period that we'd expect to find these sorts of planets with the radial velocity method. And especially if you're working with small stars, the amplitude of these spurious signals can actually be larger than the planetary signals that you're dealing with. Small stars, by the way, are even more prone to sunspots than larger stars, meaning that while working with small stars can get you a larger signal to find like low-mass planets, you really need that stellar variability. The granulation is something that there are complicated methods to deal with, but right now we just kind of have that uncertainty in our measurements. But it can be a lot of work to measure out, to model out those sunspots and ensure that what you're looking at isn't a spurious signal. Luckily for you guys, when we get to the demo or the assignment, we're only looking at really, really massive planets that have huge signals that swamp both these out. But if you're dealing with lower mass stars, you need to be really worried about them. And ultimately, that's how we arrive here. Radial velocities aren't perfect. They only work for bigger stars, or bigger planets, as you can see. And they work well when you have, well, they work best when you have short periods, but they work better at longer periods than transits do. But like I said, radial velocities aren't perfect, but they are good for a lot of things. And a lot of times they're the only method we have for really detecting all those planets out in this region of parameter space. And so they suck at times, but that's the reason they're my favorite method of detecting exoplanets. So yeah, do you guys have any questions?
Hmm. If not, maybe we can continue.
Okay. Yeah, sorry, Josh, for taking up so much time.
No worries, true. Very fun stuff. Josh, I think you're up next.
Yep.
So Josh will tell us about summer research opportunities. Go ahead, Josh.
Sure. Am I sharing screen? 1 second. Okay. Yeah, so my name is Joshua Lieberman. I am a graduate student at the University of Arizona, and today I will be presenting on summer research opportunities. So just to briefly outline this talk, I'm going to start by going over why pursue a summer research opportunity at all. And then I'm going to get into what advisors are looking for and how you can kind of market or promote yourself, and even use this self-promotion method to identify research opportunities that may not even be advertised. I'm then going to get into formal summer research programs. And finally, I'm going to go over and I'm going to review an overview of these research programs, particularly their applications, go over the timeline, and then just highlight some final tips when pursuing a summer research opportunity. So why look for a summer research opportunity at all? Well, it's a great place to get your first exposure to research. So oftentimes little experience is required, and it's a really great opportunity to decide whether or not to pursue a research career further, because really you won't know whether or not you want to do research as a job until you've actually experienced it. So this is a great opportunity to do that. And then also, really all research experience at the undergrad level, I feel, is good experience, because you can apply it to really to any field, not just astronomy. And additionally, these research experiences can be a lot of fun. You can make friends with other interns or researchers who have similar science interests, and you can kind of build a community within your field through these research opportunities. So now I'm just going to briefly touch on what advisors are looking for in an undergraduate researcher. And one of the most important things is just to have a dedication and willingness to learn. And because you're all here participating in Intro2Astro, you've already demonstrated this important step. So now I'm going to get into how can we show these research advisors, how can we show them this dedication or willingness to learn? And so one method that I used that was very effective, and it might seem a bit unorthodox at first, but just bear with me. So I used this method to obtain research opportunities that weren't necessarily listed online by essentially marketing myself. And what that looks like is first you identify a researcher whose interests align with yours. So that may mean looking up a research topic that interests you, browsing some papers in the field that you've learned how to do through Intro2Astro, and noting the authors that have, and additionally searching the directory at your current institution. Are there professors doing similar research to what you are interested in? And then you can, once you've done this, you can send those researchers or professors an email directly, what people would refer to as a cold email. And this, I feel, is kind of an underutilized method of pursuing research opportunities in the field, particularly as an undergrad. But I think it's it's a really valuable method to practice and very simple. Additionally, it demonstrates this motivation or initiative. Additionally, it's a great way to stand out as an applicant or as an interested researcher in undergrad. There's no application necessary required to send an email. And additionally, you don't have to be a US citizen to practice this method, as a lot of the research opportunities that I'll highlight later are US based and often require that you be a US citizen. But of course, the con with this method is that let's say you do identify a researcher, or there is a researcher who's interested in bringing you on. This doesn't necessarily guarantee a research position with funding, whereas the summer research programs I talk about later, if you get those, they are guaranteed to have funding. So what does this email look like? Well, so here I want to share with you a template very similar to what I would use to obtain research opportunities when I was an undergrad. And I can personally vouch for this just because I used this method to obtain research opportunities at institutions like the Keck Observatory and California Institute of Technology. So in this first section, what I'm doing here is I'm stating my intent. So you're going to state, of course, your name, what year you are as an undergrad, your institution, and then you're going to basically highlight that you're applying for these summer research positions in astronomy, and particularly you can highlight a subfield that the researcher is involved in, which I found in my experience would often pique their interest. And additionally, this last line is another great way of really making yourself stand out when you're sending these emails. And it's you can use your skills again in reading papers and highlight a particular paper or research project that this professor or researcher was involved with. And that's a really great way of getting into the research in that particular field. And so then in this next paragraph is where you basically summarize your experiences. And you can think of this as like an abridged version of your CV in email form. So you highlight what makes you a valuable candidate. And additionally, so in this example, I'm highlighting the Intro to Astronomy research workshop. And what I've also found to be valuable in this cold email approach is to name the researchers that you've worked with, because you never know if oftentimes the person you're emailing will know of these researchers, and then you already have a strong connection in that field, and that will increase the likelihood that this professor responds and offers you a position. And so then basically just in the end, you're going to restate your interest. So I'm just providing another example of that template, but filled in. So I'm just using as an example, Professor Fei Dai, and I'm writing a template as if I'm applying to summer research programs in exoplanet astronomy. And I highlighted a particular project that Professor Dai worked on involving test photometry of ultra short period planets. And in this second paragraph, I'm highlighting my experiences that are relevant to this work. You'll probably want to go into a bit more detail than I provide in your actual email, but I'm highlighting the relevant experiences that I learned from this research workshop involving the my work with test data. And additionally, I'm highlighting various hard skills like programming languages I know, as well as soft skills like ability to read scientific literature and web development. So all things you have learned over the course of this workshop. And then finally, I just changed the last section a bit. One thing that's helpful is even if this professor isn't able to offer you a position, they might know someone else who will. So oftentimes it can be useful to just ask this professor or researcher if anyone else they know, if they're looking for summer interns. So I encourage you all after over next week, just as an exercise, to try sending out one of these emails expressing interest in a research project to a professor, either at your institution or at an outside institution, and feel free to share the outcome in the Discord. So and then just one key thing to remember regarding this approach is really just don't sell yourself short. That oftentimes as undergrads, we feel like we don't have as much experience as we actually do. But even just through this workshop alone, you've already learned a ton of skills that make you marketable as a researcher that you can highlight in your applications. So moving on to, these are more, I guess, at least in the US, these are well-known summer research programs to highlight. Although with the important caveat that 2 of these 3 really are limited to US citizens. So the first is called the REU. It's funded by the National Science Foundation. And these are called research experiences for undergrads. The second one, SURF, is a summer undergraduate research fellowship. And the particular example to highlight for SURF is Caltech, where they offer a SURF program hiring multiple researchers a year, or hiring multiple researchers over the summer. And with this one, it's important to point out that you don't need to be a US citizen to apply. And additionally, the application process for the SURF in particular looks a bit different in that you apply together with an advisor at the institution in the case of Caltech. And that's where, again, that emailing method I showed, that really helps because you can reach out to a researcher you're interested in working with, and then they can help you on this SURF application. And then finally, I want to highlight that NASA's Jet Propulsion Lab, they hire hundreds of undergraduate interns every summer. So there are a lot of opportunities there to get experience as a researcher. However, this is these internships are more difficult to obtain as a foreign national. Although I do know of a few cases of interns from abroad working at JPL. So now, so here are a few examples of where you can find these opportunities. And again, these slides will be posted after the workshop. And so these 3 just link to the programs I talked about. And then this 4th one is a really valuable database for looking for research opportunities, mainly in the US, I believe, but it's called Pathways to Science. And I highly recommend browsing this because it's a very valuable resource for finding positions both during the school year and over the summer. And additionally, I highly encourage you to look into summer research experiences at your own institution. And again, you can send these emails of expressing your interest in a certain professor's research. Additionally, it's many institutions also offer summer funding opportunities. And these are great resources to utilize in cases where you're offered an internship, but the researcher isn't able to pay you. And so in this way, you can get your home institution to pay for the internship. So just going over the general components of one of those applications that I listed, being say REU, SURF, or the JPL application. Typically, at least for REUs, the applications are posted in the fall and they're due around early February. And a typical application will require a written statement summarizing your interest in research experiences, as well as your CV or resume, and then a few recommendation letters along with unofficial transcripts. And you'll often receive a decision around March or April, and these summer programs in particular will often start in late May or early June. So regarding the recommendation letters, because this is often challenging for undergrads who are first starting out. So just a few pieces of advice. One is that when you're asking for a recommendation letter, it's important to ask for the letter early. Some examples of people you can ask for recommendation letters are professors you recently took a course with, or maybe previous research mentors you've had, or even employers in your work. And so in asking for these recommendation letters, you'll typically want to write a polite email and stating what program you're applying for and when the deadline is. And additionally, it's valuable in requesting a recommendation letter to the writer to remind them of your connection. So highlight, and this is also in this email, this is an opportunity to highlight certain elements that you want the writer to talk about. So if you are part of a large class/research group, maybe you can highlight a certain project you worked on or a particular assignment to help the professor kind of remember who you are and also write a more valuable recommendation letter. So just a few final pieces of advice regarding seeking research opportunities. I encourage you to look for opportunities early. I feel really it's never too early to start looking or asking around. Again, the worst that can happen, particularly with that email approach, is you just don't get a response. Or the professor might say, just email me back in a few months when I have more of an idea of whether or not I'm offering. And also, it's important through this process to keep an open mind. I highlighted before searching for research positions that you're interested in, but really it's hard to really know exactly whether or not you're interested in a certain field until you actually start doing it. So keep that in mind while you're applying as well, where even if an advisor is conducting research or you're applying for a position that isn't exactly in the field you are interested in, you may still end up really enjoying it. So that's a valuable thing to keep in mind. And finally, as I've kind of alluded to before, it's important to tailor your application to the position you're applying for. So for example, if you're applying to a position doing exoplanet research, it's more valuable to highlight your related experiences in that particular field. And finally, just stay curious. This will serve you really well as a researcher moving forward and help you remain excited about your research for years to come. So yeah, that's it. And I want to thank you for listening.
Thank you so much, Josh. Do you have any questions here? Well, so Quiddy asked how to do a good personal project in case you don't get a research project.
So I feel that as far as good personal projects go, you can participate in more opportunities like this Intro to Astronomy course. And I can highlight a few in particular that are also offered. One I have in mind immediately is called Instro2Astro, which is also a workshop with a similar goal to this one, where it's basically teaching you coding, getting up to speed, and also connecting you with some of the, again, some of the top researchers in the field of astronomy. And so these types of workshops are intended for people in these positions who don't necessarily have a lot of experience yet in research and are looking to get started. So
Yeah,
I don't know if
I do.
that answers your question, but
Register now on bit.ly/intro2astro 2024.